Okay, perfect. Good afternoon, everyone, and thank you for the nice introduction. I'm very glad of being here, let's see, this afternoon to talk about a bit my research that started in electronics cooling and then shifted towards the aviation sector. And we will see today that the two fields seem very different from each other. In reality, they share some engineering problems that are mainly connected, for my case, to thermal problems and cooling systems. In fact, when we look at data center and aircraft engines, we tend to think they are two very different technologies, and they are covering very different engineering subjects. In reality, this is not true. So we will see today that both these fields are now growing, and can you hear me? Yes. Both these fields are now growing increasingly, and the power demand is increasing, and this has a cost on our climate. So they both have a huge environmental impact. Not only that, they also share some engineering challenges, such as dissipating higher and higher heat loads. So starting from the data center industry, there's an increasing demand in internet traffic and cloud-based services, as well as processing or storage. And this is driving the energy demand, pushing and increasing almost exponentially. And we can see that data centers, that is the green portion, is taking a larger and larger slice in the forthcoming years. Very similarly, the aviation sector is, despite you can see the valley during COVID years, is expected to grow till 2050, and more or less the average estimated is 3% per year. This increase in demand in both sectors is, as I said, having a huge environmental impact. We can see in the plot that data center industry is leveling the aviation sector in terms of CO2 emissions. This both contributes to 2.5 up to 3.7 estimated % on CO2 emissions. So this is huge. If we look at data centers, almost 40% of the energy consumption is for cooling. It means that the increasing demand makes servers and data centers hotter and hotter, and essentially 40% of the electricity bill is just to keep them cool. Similarly, aviation, as I said, has a huge impact on the environment, and probably even larger than data center on the global warming, due to what are called non-CO2 effects. So CO2 is not the main only pollutant. We must consider also recent studies suggested nitrogen oxide or contrails, as you can see in the picture. So in order to, let's say, tackle the problem of environmental impact of these two industries, and in particular now I will focus on aviation, we need to think about a mix of solutions to bring aviation to zero emissions. And this is very important for me to communicate. It's an extremely challenging task. It's not easy, and it includes many different challenges, and we will see also thermal ones. So as I said, in order to cut the CO2 emissions, as we can see in the plot, if we don't act and we keep flying with the current aircraft, the CO2 is just expected to grow and increase in the forthcoming years. This is the top line on the plot. Although we need to, industries and governments have agreed to what is called net zero emission. So it means that by 2050, the CO2 has to cut to zero level. And to achieve that, we need to follow different ways, different solutions. The first one is, how do we design and fly planes? So there's still improvement in engines, gas turbine efficiency, in aerodynamics and materials, but also on infrastructures and routing. or for example, packing more passengers on board, and Ryanair is particularly on top for that. The second big, you'll see the second big share is given by sustainable fuels. You might have heard of those. They come from waste, organic waste, or other green sources, but they are expensive, and currently aircraft companies don't use much sustainable fuels, but they will have to be integrated in the strategy. And the third point that is the most interesting for me and for my research is thinking about new and emerging technologies, meaning new way of essentially create trust. You probably heard about the use of batteries or hydrogen or fuel cells. We will talk a bit about that. But what I want to stress is that all of these emerging technologies will face the problem of dissipating larger and larger heat loads. So we have to think about novel cooling solutions that might also recycle heat generated on board. So starting from batteries, these can be employed for electric propulsion, so that will be a fully electric aircraft, or for other systems on board, such as the environmental control unit, for example. And this is usually referred as more electric aircraft. The big challenge associated with batteries, probably the first one, is that they are currently still limited in energy. This is where we are now, the blue dot. So we are about 30 times less than Jet A, kerosene. That is the current fuel. And there are some prototypes. This, for example, has been proposed by Aviation that bring 10 people, 10 passengers for 200 kilometers. So this is still a bit far from achieving zero emission. And related to batteries, there are, of course, other challenges, as recycling batteries once their lifetime is ended, but in particular, overheat. So batteries need to operate in a very specific temperature range, not too hot, but also not too cold. And if they overheat, their efficiency drops, and they eventually fail too. So cooling is, of course, important for batteries. If we move towards hydrogen, that's one of the most hot topic at the moment in aviation. This can be used as a fuel, so in a combustion mode, we can essentially fly almost traditional turbines with burning hydrogen instead of Jet A. But hydrogen can be also combined with a traditional gas turbine. Those are usually hybrid aircrafts, or can be associated also to fuel cells that produce electricity that eventually supply electric motor that drives our propellers, as you can see on the right-hand side. These two nice images are coming from Airbus. It is on the way to develop some hydrogen in different configuration aircrafts or fully electric, driven by fuel cells. Of course, these are brilliant ideas and very promising solutions, but again, they have some challenges to be solved first from us. And first of all, these new propulsion systems might have penalties in terms of mass and drag. And in the new systems, the heat exchangers components, such evaporators or condenser, will play a crucial role on the overall efficiency of the new propulsion system. Fuel cells, similarly to batteries, generate huge amount of thermal heat fluxes that needs to be dissipated and possibly reused. So another interesting area for hybrid propulsion is, can we use the heat coming from the turbine or the evaporator to reuse it and maybe fuel or heat something on board? And last, but probably also very important, is the cost of producing hydrogen. Nowadays, it's still very expensive to produce green hydrogen. So essentially, we've seen different possibilities to achieve net zero flights. These can be fuel cells, batteries, or hydrogen-related technologies. And all of these will create higher power and thus higher heat loads on board that will need to be dissipated. It is estimated that future cooling system will require to be powerful in terms of megawatt compared to kilowatt. So we are 3 orders of magnitude more. So the question that links a bit my past and current research is, can we maybe bring some cooling technologies that have been developed for data centers or electronics on board of future aircraft, or adapt them to work for future aircraft? And maybe I can play this video. Maybe that is? No, sorry. Okay, this is just to show you an example of, perfect, thank you, an example of immersion cooling. This is now used in some data centers that are transitioning towards greener cooling system, where you can see the server and the electronics is directly merged into a pool of the electric refrigerant, non-toxic and dielectric. The hotspot on the motherboard, that are usually the CPU and the GPU, you can see are covered by bubbles. So essentially, the refrigerant evaporates close to the hotspot, creating what is called two-phase flow, so a mixture of liquid and vapor bubble. And this system can be, of course, maybe implemented on future aircraft, and can be also maybe utilized for other components on board of a future aircraft. What is interesting of two-phase flow is that thanks to the latent heat of vaporization, so the phase change process require a lot of energy. So thanks to this, we can achieve much higher heat transfer rate compared to the traditional air cooling, liquid cooling, that means only liquid. And we can see that two-phase flow can achieve almost 100 times more of dissipation compared to air cooling. This means that if we have a much higher power to dissipate heat, we can shrink the system down, make more compact and lightweight solutions that are very important for aircraft too. So in this picture, there's an example of a project I collaborated in Nokia Bell Labs. This was a micro evaporators. Imagine these channels are the size of my hair, so a few microns, and a liquid refrigerant entered through the evaporator that is in contact with the CPU of the servers, start evaporating, so we have two-phase flow across the channel, and then goes out in a two-phase mixture. Now, in relation to two-phase flow, there are still some very exciting research questions that I'm trying to address. This is a nice video of my bubbles, and one of the unexplained phenomena is still how do bubbles transfer so well heat? There are different mechanisms involved. One of these, and probably the most interesting and not fully understood, is what is called micro-layer evaporation. So you have, at the formation of the bubble, you have a layer of liquid that is forming underneath the bubble between the surface and the vapor interface. And this micro-layer evaporates and seems to be responsible for the very good heat transfer rate. Another interesting research question that we are trying to address is, what is the interaction between the bubbles and the surface? Does the surface condition have an impact on the transfer, possibly also on pressure drop? So can we think about smart surfaces like enhancing roughness or machining micro or nanostructures on the heated plate in order to enhance heat transfer and eventually also reduce pressure drop, that means consumption? So I hope I covered a bit what I've done in the past years here in Oxford and now in Delft. This map is not an internet network, but this is a flight network, and a bit links my two research. So hopefully we will find novel thermal management solution for sustainable aviation. Thank you very much.
Chiara, thank you so much for another fascinating... God, bubbles get absolutely everywhere. We're kind of almost like the Department of Bubbles. We do have a few minutes for questions. So, gentleman in the front row, see if I can get the microphone to you.
Oh, yeah. I can hear in case.
Must be. I'm intrigued. If you're going to generate gas, then presumably there's some work to be had by the recondensation. Is there a viable opportunity to use some of the energy that's dissipated to produce work?
Yes, so that's a very nice question. In fact, there are some prototypes and studies going on that use also what is called the Meredith effect. So the heat exchanger in the aircraft acts also as an extra propulsion system. So by using temperature gradients or phase change, you can create essentially additional thrust and maybe use it as potentially create, essentially improve the efficiency and improve the thrust. Yes.
Do you have a loud voice?
So with regards to the induction of the vapor phase in the cooling system,
yeah.
is there sort of cavitation of the surface?
Yes. So one of the main limitations of two-phase flow system is that if the heat flux becomes too high or there's some failure in the system, then you have a vapor layer covering the surface, meaning this is called dry out or critical heat flux. And at that point, your heat dissipation goes completely down. So that is something that is one of the bottlenecks for this system, need to be really well understood. If that replied to your question. Yeah, there's also, in fact, like cavitation effect in turbines, right? Or in components, yeah. So there is also something like this. In particular, when you study coated surface or engineered surfaces, you also need to account for the degradation that this might create on the material, yes. Great.
Sorry. Yeah, thanks. Thanks, really interesting talk. I had a question. If you're trying to liquid cool the elements and you're putting it on a plane, are there any weight constraints? Because now you're adding something quite dense onto a plane and
yes,
costs more fuel to lift off, create lift, etc.
Yes, that's absolutely a point to consider. As I try to show, two-phase flow though has a 100 to 1,000 more heat transfer capability. So it means that your system volume goes down by even more because it's squared. So probably that is a nice counterbalance to think. And anyway, air cooling now maximum capacity is 10 watt on centimeter square heat fluxes, and these will be go 2 kilowatts. So still we have to cool them.
Great. I think we have time for one more, two more quick questions. I'll get the microphone to you.
Nice.
Hi, I'm Katie Huang. I was at Alumni 96. My question's around sort of urban applications to the data center. So we've read in the press, combining with swimming pools. I was just curious whether you've looked into other urban applications and where you think it could be more effective.
Yes, thank you for the question. So two-phase flow cooling has also been investigating for smart building and to improve efficiency of smart buildings. And in fact, I still have a collaboration with Nokia that is in a way studying that by looking in reality at the telecom center rooms. And finally, the climate, the climate inside the telecom room can be approximated as a building in the end. So we are doing some studies that include also building infrastructures and efficiency of buildings, yes.
Thank you. And we have one more question.
Tony Lloyd, does ammonia have any potential application as a jet fuel?
Yes, ammonia is being studied as potential fuel, absolutely. I would say Europe is being more inclined towards hydrogen. This was maybe pushed more by governments and policies too, while the United States are definitely including ammonia in their portfolio. And I know aerospace companies studying ammonia, yes, absolutely. Even ammonia as coolant system in reality, because it has very good thermophysical properties, so it can also be used for cooling systems. There's very high capabilities.
Thank you very much indeed. Thank you for the interesting questions, and thank you again,
it was very
Chiara.
nice.
Thank you.
Thank you.